It is 3 in the morning in the North Atlantic. A container ship the length of 4 city blocks is pitching through 30-foot swells. On its deck, 10 stories of steel boxes are stacked so high they block the horizon. Each one weighs 30 tons. To anyone watching from shore, the assumption is that sheer mass holds them in place. That gravity alone locks all that weight down. That assumption is completely wrong. Those containers have almost nothing physically connecting them to the ship. In a bad storm, they don't just slide, they twist, buckle, and launch. One container lost overboard becomes an invisible reef, waiting for the next vessel that crosses that lane in the dark. Here is what most people picture when they imagine cargo securing: bolts, welds, heavy permanent hardware, the kind of industrial fastening that holds a bridge together or keeps an engine mounted to a frame. What is actually holding those containers in place is a system of twist locks and lashing rods. A twist lock is roughly the size of a large padlock. It slots into the corner fitting of a container and rotates to engage the one above it. The lashing rods are diagonal steel bars running from the side of the stack down to anchor points on deck. And the entire system, every single component, is designed to be installed fast and removed fast, because that container will be in a completely different port in 72 hours. The goal was never to make the containers immovable. The goal was to make them removable at speed in every port on Earth. Permanent fastening would make global containerized shipping impossible. So, the entire securing system was engineered around a constraint that had nothing to do with storms, and then it had to survive them anyway. The securing system is a consequence of logistics, not just physics. And once that distinction lands, everything else about how this works starts to make a different kind of sense. So what is actually happening during a storm? When the ship rolls, the containers do not roll with it instantly. Inertia wants to keep them where they were. The lashing rods on one side go into tension, the rods on the other side go into compression, and both things are happening simultaneously across every stack on the ship. But here is the piece most people miss. The geometry of the stack matters far more than the weight. A taller stack multiplies the leverage force at its base. It is the same physics as trying to push over a tall bookshelf versus a short one. The taller version requires dramatically less force at the top to generate a dangerous moment at the bottom. Containers near the top of a high stack are experiencing lateral forces that would stagger most people if translated into something visible. And then the ship itself makes it worse. A modern container ship is not rigid. It flexes and twists slightly in heavy seas, the bow and stern moving slightly out of phase with each other, and that flex travels up through every stack from the keel upward, adding a torsional load the lashing rods were not sized for in simple rolling calculations alone. The ship is not just a platform, it is a moving, bending structure, and everything locked onto it moves and bends with it. Now here is the part that genuinely inverts common sense. The assumption is that bigger ships handle this better. Bigger means more stable, heavier, harder to push around. And for the crew, that is mostly true. But for the cargo, the math changes. Ultra-large container vessels, ships carrying 20,000 containers or more, have a much wider beam, which means they roll more slowly. Slower roll sounds safer. It sounds like the problem is shrinking. But a slower roll with greater angular momentum means the lashing gear can actually experience higher peak loads than it would on a smaller, faster-moving ship. The energy is the same. It just arrives more slowly, which means the peak tension in each rod holds for longer before the ship begins to recover. The assumption that bigger is always safer is exactly wrong under this specific condition. It took the industry an uncomfortable amount of time to fully absorb that. And it is still reshaping how the newest class of vessels approaches stack height limits and lashing certification. Every container ship that leaves port carries a document called the Cargo Securing Manual. It is specific to that vessel, not a generic industry template. It calculates maximum stack heights, acceptable weight limits per bay and per row, and required lashing patterns for different sea states. Before a ship loads a single box, stowage planners, people, mostly working shoreside, using specialized software, calculate the position of every container. Not approximately, every one. A forecast of heavy weather in the North Pacific does not just change the route, it changes where heavy cargo gets placed in the stack. Dense, heavy containers go lower, lighter loads go higher. The position of every box is a structural decision with engineering tolerances behind it, not a logistics preference or a space-filling choice. Think back to that image of the ship from the opening, 10 stories of steel stacked against a dark sky, looking like warehouse shelving bolted to a hull. What looks from a distance like a logistics pile is actually a three-dimensional structural calculation that someone ran on a computer the day before departure, and every storm the ship encounters is a live test of whether that calculation was right. But even the best load plan runs into a problem that no stowage calculation fully solves. Parametric rolling. In certain wave conditions, a ship's natural roll period can synchronize with the period of the waves hitting its bow. When that synchronization happens, each roll builds on the last one. A ship that was rolling 8 degrees is suddenly rolling 20, then 30, then more. It can happen in under 10 minutes with almost no warning, and it does not require a particularly large wave. It requires the wrong frequency at the wrong moment. The wave does not need to be big, it just needs to arrive on the right schedule. And the counterintuitive part, the part that exposes a genuine gap between instinct and operational reality, is what trained officers are supposed to do when they recognize it. The instinct, especially with charter agreements, port windows, fuel costs, and schedule pressure in the background, is to push through. Hold speed, hold course, make progress. The correct response is the opposite. Reduce speed, change heading, break the synchronization, even if it means pointing sideways to the destination for hours and losing an entire day of progress. Operators have lost hundreds of containers in parametric rolling events while following every other protocol correctly. The weather was not outside the ship's rated limits. The lashing was properly installed. The load plan was sound. The storm was not the problem. The resonance was. In 1998, a container ship called APL China was crossing the North Pacific in severe weather when parametric rolling hit. The ship lost more than 400 containers overboard in a single event. Containers went into the water. Lashing rods failed under loads they were never designed to survive. At the time, it was one of the largest single cargo losses in maritime history. The investigation that followed was not just about that ship or that crossing. It revealed a systemic gap. The maritime industry's operational understanding of parametric rolling was incomplete. The lashing standards in place had been designed against a different threat model, one that assumed the primary danger was a large wave hitting a ship broadside, not a resonance condition that builds quietly over minutes in weather that looked survivable on paper. APL China forced a reckoning. New IMO guidance followed. Lashing standards were revised. Research into parametric rolling, which had existed in academic literature for decades, was finally taken seriously at the level of actual operations. One crossing, one storm, one ship, and the entire framework for how the industry understood cargo retention had to be rebuilt from the wrong assumption up. Go back now to a container ship sitting in port. Those diagonal orange and yellow rods running across the faces of the stacks, most people assume they are part of the structural framing of the containers themselves, or some kind of permanent scaffolding built into the ship's design. They are lashing rods. They are doing active, calculated tension work, and their angles are not decorative. They are positioned to resist the specific lateral and longitudinal forces the cargo securing manual identified for that vessel in that loading condition. The color differences are not paint choices or manufacturer branding. They often indicate different rated braking strengths, so a trained lashing crew knows at a glance whether the right rod went in the right position, and the workers moving quickly around the base of those stacks as cranes swing the next box into position, they are inserting and removing twist locks by hand, one corner at a time, at speed. There is no automation at most terminals for that step. The mechanical connection between two 30-ton steel boxes is made by a person with a handheld tool in under a minute, repeated thousands of times per port call. The system that keeps those containers on a ship through a North Atlantic storm at 3 in the morning begins and ends with a human hand turning a lock the size of a padlock. The system is not solved. Every cargo securing manual has a sea state limit, a point beyond which the math no longer holds and the hardware is not rated to perform. Misdeclared cargo weight is a persistent, documented, industry-wide problem with real structural consequences. A container declared as 10 tons but actually loaded to 28 breaks the stowage calculation for the entire bay it sits in, and potentially the bays around it. The ship's officers cannot verify the declared weight of a sealed container once it is on board. They are working from paperwork. Modern vessels are beginning to install strain gauges directly on lashing rods, feeding live tension data to the bridge so officers can see in real time when a stack is approaching its design limit. Some ships now carry motion prediction software that models parametric rolling risk against live wave period data and can flag a recommended course or speed change before the resonance has a chance to build. The technology is catching up, but roughly 1,000 to 2,000 containers are still lost at sea every year globally. The visible failures generate insurance claims and news coverage. The near misses, the ships that slowed down in time, the officers who changed course before the synchronization locked in, the load plans that held because someone got the weight declaration right are just part of an operational texture that nobody outside the industry ever hears about. That container ship rolling through 30-foot swells in the middle of the night is not a chaotic pile of metal held together by mass and luck. It is a live structural calculation, running continuously, tested by forces that change every few seconds and were anticipated, imperfectly, honestly, with known margins and known gaps, by engineers and planners who never saw the specific storm the ship is now inside. Every lashing rod is carrying a load its designer anticipated. Every stack height was a decision made hours before the first wave hit. Every course correction the officer of the watch makes is either working with that calculation or against it. The containers stay on because the forces were understood, modeled, and in most cases, most of the time, just barely managed. Here is what the next question looks like. The containers that do go over the side do not always sink. Many of them float just below the surface, invisible to radar, drifting across major shipping lanes for days or weeks. The maritime world has a container tracking problem most people have never heard of, a warning system that is genuinely incomplete, and a set of decisions about when a lost container is no longer a navigational threat that involve far more uncertainty than any port authority would publicly admit. The storm does not end when the containers leave the ship. In some ways, that is when the real problem begins.